All right, welcome back to your last Unit 3 video. Hold back your tears. You'll notice I did not put everything from what we're learning onto these videos. Some of these things are just not well explained without someone in front of you. So some of it you're going to have to do some reading, go through your PowerPoint. But the last topic that I do want to cover on video is half-life. Okay? Half-life is one of those things that really is simple, and yet we always let it confuse us. Half-life, we discussed this in class, is basically how long does it take for half of something, okay, to break down, to decay. If you go back into your PowerPoint, you'll see that we talked a lot about radioactive decay, okay, and what radioactive means and how it happens. So read up on your PowerPoint, but remember that half-life is how long it takes for half of something to go away. In class, we talked about how different isotopes of uranium and potassium and thorium have crazy long half-lives, okay? 704 million years, okay? 48 billion years. There's some long ones. But most of the time, when we talk about half-life, we are going to talk about carbon because that's what's used in radioactive dating. So the 2-second version of this is most of the carbon on Earth is carbon-12. Okay, that's what most of us have, basically making up all of us. We do, however, also have carbon-14 that we get from plants. So when we're alive, we're eating plants. And I know what you're thinking. You're thinking, I don't eat any salads. All I eat is my hamburger and my steak. Well, good for you. You're eating a cow. You know what your cow eats? Grass. You are getting carbon-14 from plants. So when you are alive, there is a fixed ratio of carbon-14 to carbon-12. Okay, this stuff stays in a ratio. We're not going to get into that ratio. It doesn't really matter. But once you die, you stop eating. Some of you, that might be the only time you stop eating. But once you're dead, your carbon-14 levels drop. Okay, your carbon-12 doesn't drop at the same rate as your carbon-14. Your carbon-12 is much more stable. But you're not eating, so you're not taking in more carbon-14, so that level's drop. So what we do is we try to measure the ratio and look at how much carbon-14 to carbon-12 that you have left. Okay, determining half-life is very, very simple. The carbon-14 half-life is 5,715 years. You do not need to memorize that. It will always be given to you. So the questions you may see is that you find an artifact, okay, that has 1/8 the modern ratio, and I want to know how old it is. So the steps are very simple. I don't know why that said ration. The steps are very simple. Step 1 is you want to figure out how many half-lives have gone by. Okay, so determine the number of half-lives that are gone. Your second step is really easy. You're going to multiply that number of half-lives by the length of the half-life. Because remember, it's not always carbon-14. That's just the example we use. So let's look at our problem here. Okay, our artifact has 1/8 the modern ratio. So if they're giving me a fraction, I'm going to assume I started with 1. After 1 half-life, how much do I have left? Correct, I have half. After another half-life, how much do I have left? I have 1/4. Because remember, half-life is all about half of what you have going away. All right? After another half-life, I have the 1/8. That was the magic number. So if I count, I went through 3 half-lives to get to 1/8. My second step was multiply it by the length of the half-life. Well, each half-life was 5,715 years. That means for this to break down took 5,715 years. This took 5,715 years. This took 5,715 years. Okay, so my artifact is 17,145 years old. Now that's an estimate, okay? This isn't effective up to like, no, it's 17,146 years old. That's not what we get into here. We get into ranges, okay? Another way you may see this, and again, these are in your PowerPoint, so you can check them out. The half-life of radon, all right, we're just going to use one of the isotopes of radon. We'll use radon-226. That half-life is 1,599 years. That's a short one. So let's say the question this time says, how many years are needed, and again, looking at your PowerPoint might be helpful because I'm skipping words here, for 15/16 to decay, for 15/16 to be gone. So think about it. If 15/16 are gone, how much do I have left? I have 1/16. So we're going to go through the same process. They're giving me a fraction. I'm starting with 1. I'm going to go to a half. Then I go to a fourth. Then I go to an eighth. Then I go to a 16th, which was my magic number. So how many half-lives have gone by? 4 half-lives. Each one is 1,599 years. And that would be your answer. Okay? Again, half-life problems are not that difficult. They really aren't. Okay? Here's another one. Assume the half-life is 3 minutes. Ooh, that's a quickie. Okay? How long will it take for 16 milligrams to become 1 milligram? You got to think about this, okay? Now, I'm not given a fraction on this one, so clearly I'm not starting with 1. But I got to figure out how many half-lives have gone by. So if I started with 16 milligrams, after 1 half-life, how much do I have left? I have 8. Then another half-life gives me 4. Another gives me 2. Another gives me 1. So that happens to be 4 half-lives that have gone by. Each one was 3 minutes long, took 12 minutes. All right? Half-life problems can really look difficult sometimes, but what it always boils down to is how many half-lives have gone by multiplied by the length of the half-life. Okay, we start you in different places, but if you can remember that, you can get any problem that's given to you.